Okay.
Okay, good afternoon. Our speaker today is Letizia Bugiani, who started her PhD just a couple of months ago here under the supervision of Sirio Belli, with whom she also got her master's degree here in Bologna in October. And starting already from last spring, she is part of the Blue Jay collaboration, international collaboration, studying galaxy formation at cosmic noon. And that's also the topic of our talk today. Please.
Yes, thank you. Hello, everyone. Today I'm going to talk a bit about, in particular, star formation quenching in galaxies observed at cosmic noon with the James Webb Space Telescope. In particular, my focus will be mostly on quiescent galaxies because those are the ones that I studied more in depth. But anyway, I'm going to present a bit of the work that I'm currently doing. So there's going to be a lot of stuff unpublished. And we are going to look at how the James Webb Space Telescope in particular is revealing new things about the topic of star formation quenching. So let's first start with what we mean by star formation quenching. Well, this is a kind of umbrella term for a lot of different phenomena that can happen in a galaxy and that can inhibit or prevent altogether the formation of new stars. And it is tightly linked to the gas cycle in a galaxy. Roughly speaking, very roughly speaking, of course, stars form because gas is accreted from the galaxy, from outside by the galaxy. Then the gas in the halo needs to cool down in order to go down to the disk of the galaxy, where if it is cooled down enough, it can collapse into new stars. And of course, we can have also a feedback mechanism that create, for example, stellar winds or AGN feedback mechanism that can also eject the gas from the galaxy itself. And at each point of this very general mechanism, we can have inhibition of star formation, so star formation quenching, because of course we can have that gas is not accreted by the galaxy, so what we call cosmological starvation. But if it is accreted, it could also not cool down from the halo, and this may be due to, for example, virial shock heating or AGN feedback that keeps the gas hot in the halo. But it could also be that the gas is cooled in the disk, but it does not form stars. This could be due to a lot of different mechanisms, also magnetic fields, again, AGN negative feedback, some morphological phenomena. Or we could have a lot of star formation altogether that basically exhausts all of the gas in a very rapid time scale, which is of course a starburst phenomena. And this could also be, for example, due to mergers. So after a merger, we could have a lot of starburst and the gas is over. And of course, we could have that the gas is actually being ejected from the galaxy. By, for example, as I spoke before about stellar winds that can eject the gas from the galaxy, or, for example, AGN feedback, ejective feedback. So the main thing is that we have to study the gas and the gas cycle in galaxies in order to understand the star formation quenching. Also, star formation quenching, of course, is fundamental for the study of galaxy formation and evolution, and in particular for the evolution of quiescent galaxy, which is the galaxies in which I am mostly interested in. But it is also important, for example, for some other cosmological observables. For example, we need the star formation quenching to explain the discrepancy that we see between the stellar mass function and the dark matter halo mass function in galaxies. This is a plot that I have taken from this review from 2017. In black dashed line, you can see the article calls it cosmic baryon function. That is basically the dark matter halo mass function, but scaled with the baryon fraction. So it is basically how we would expect the mass to be distributed in galaxies. But then if we look at the observations, which are the black points, the empty black data points, we see that there is a discrepancy that is mostly visible both at the low mass end and the high mass end, in which we see less stellar mass that we would expect. And this is due to star formation quenching that is basically thought to be feedback from star formation at the low mass end, and feedback from AGN, or maybe due to mergers at the high mass end. And here we have the colored tracks. Those are actually cosmological simulation that all have implemented this kind of feedback and star formation. And in fact, for example, in cosmological simulations, we have that feedback from IGN works really well in quenching star formation in galaxies at the high mass end. But we are still missing the definitive observatory proof of this fact, especially, as I said, at the high mass end, where the most massive quenching galaxies are. So here we have the new player, JWST, and this can help to look at galaxies in the cosmic noon, especially massive galaxies at cosmic noon, for which we are now able to look at a window, which is the near infrared window, which is of course the rest frame optical window in the rest frame of the galaxies, which was basically really difficult to observe before. For example, I have here, in terms of star-forming galaxies, a redshift 2.29, and the upper part is a spectrum obtained by Keck spires with 2 hours per filter on a ground-based telescope, which is 10 meters large, and the one above is below is the same galaxy, but observed with NIRSpec aboard the JWST for 50 minutes, with of course a much smaller mirror. So you can see from this example how much better is the resolution that we get, the sensitivity of JWST. And you can see there is no, the noise is very low, and also the spectral range is much more extended. So this is where the Blue Jay survey comes in. It is a spectroscopic survey conducted with James Webb. It was allocated 46 hours of observation. It's a cycle 1 observational program, and observed the 147 galaxies at redshift around 2. And here you can see they are all in the cosmos field. We observed galaxies with a wavelength coverage between 1 and 5 microns, so we have really long spectra. And here you can see the angular extent of our targets with respect to the slits of the MSA, which is the macro shutter assembly aboard the NIRSpec. So in this 147 catalog of galaxies, we selected 22 quiescent galaxies using UVJ, rest frame UVJ colors. Here we have the selected galaxies. This one was an outlier, and it was subsequently eliminated from the sample, and all of them are very massive galaxies with the stellar masses higher than 10 to the 10 solar masses. And this is an example, one of the best spectra that we have. And I don't know if you work with high redshift galaxies spectra, but this is an incredible spectra, especially for a quiescent galaxy. We can see very well the absorption lines, but we can also see some emission lines, which are the ones that I have highlighted because there's the ones in which I was interested in. And of course, from the quality of this spectra, we can get a lot of things. We can get the stellar continuum fitted. We fitted it with prospector, which is Bayesian stellar population fitting code. And of course, from the stellar continuum, we can get a variety of quantities. We can get the redshift, the stellar mass, something about the stellar population history, metallicity. But we can also see here, I don't know if you see it as well, but there is also some absorption lines that can be seen from neutral gas in excess with respect to the stellar continuum. And this was studied particularly by Rebecca Davis, which is another researcher in the team. And what I focused on, and what I will be talking about a bit more in depth, is the emission lines from ionized gas, which we weren't actually expecting to see this many emission lines from ionized gas, considering that we are looking at quiescent galaxies. So these are some of the fits that we have done at the start on emission lines, and we tried to fit all of the emission lines with using single Gaussian profiles. And the very surprising thing, and I think the first result of this work was that only 4 galaxies of 22 do not have any detected emission lines. For detection, we counted a signal to noise ratio higher than 3. So this means that not only we can see these lines, but there is ionized gas in this galaxy. So there is a source of ionization that is still going on. And this, of course, is made possible by the sensitivity of James Webb. I have here an old study from my supervisor from 2019, and this is the spectra of 18 galaxies, quiescent at redshift around 2, observed with small spire. And as you can see, they were only able to get a detection by stacking them together. And this is one of the lowest signal to noise ratio in the Blue Jays quiescent sample. And as you can see, we have also a difference of 2 orders of magnitude in the flux. That one is 10 to the minus 20, and this is 10 to the minus 18. So I think this really shows the power of James Webb. But anyway, the fact that we have emission lines means that we can measure emission line ratios, and we can classify these galaxies using line diagnostic diagrams. These, if you do galaxy evolution, are really very much used, but if you don't know, they are basically diagrams that use the ratios of different ionized gas emission lines in order to investigate which is the underlying ionization source. In this case, we have the green line, that's called the maximum starburst line, and beyond the green line, we cannot explain the observed ratios by only considering ionization due to young stars. We have to consider ionization due to an AGN inside of the galaxy. So as you can see, my quiescent galaxies are the red points, and they are mostly found on the AGN power side of the diagram, which is in itself strange, because first it's strange that we can fit normal quiescent galaxies on this plot at all, because we have now ionized gas emission lines, and we can do that. But also we did not expect, because they were apparently they are all normal galaxies without any active nucleus. There's one outlier that is a star-forming galaxy, and these are other alternative line diagnostic diagrams that all show the same thing. In blue, we have the other the rest of the survey. This is another one which is not well known, but it's very useful because I can fit more points on this, because it's basically, it only uses the H alpha and M2 lines. So it's useful if we only have, for example, these 2 ionized gas emission lines. And here we can see again that the quiescent sample is all on the AGN powered side of the diagram, apart from the 2 galaxies which are classified as retard galaxy. And this means that basically the ionized gas emission that we see in them can be explained by just considering ionization due to old and evolved stars. But anyway, at the end of all of this classification, we have that we can classify more than half of the sample of the quiescent galaxies. And of these 22 galaxies, we have a great majority, 67% of them, that are actually hosting an AGN. And this is very surprising, considering the fact that none of these are detected in the X-rays. And I'm still going through the archives, but they are not classified as AGN anywhere else. So they are classified as normal galaxies as far as I know. I think the most egregious example is this one, 18977, which this is just a portion of the spectrum, but you can see clearly from the spectrum by eye that this is a broad line AGN, because look at the broad profile under H alpha. This is clearly a borderline AGN, but this is not detected in the X-rays. So we have a population of low luminosity AGN that wasn't detected before. Another even more surprising result is that in 4 of the galaxies which we classified as AGN, we can actually fit 2 components to the emission lines. A broad component and a narrow component, which is the red one in this case, and a broad shifted component, and which is the mark of outflows, ionized gas outflows. And this is surprising, of course, but we find in this 4 galaxies ionized gas that is actively leaving these galaxies with high velocities. And this is the other 2 examples. This is the galaxies that I showed you before. And I think you all noticed that the fit wasn't really that good before. And it's because there is actually a second component that couldn't be fitted using a single Gaussian profile. In all of these galaxies, there is not enough star formation to really explain these powerful outflows, and there are no obvious signs of mergers going on. So the only plausible explanation for the presence of these outflows is AGN feedback. Not only, last thing, we have that not only we see outflows in the ionized gas phase, but we see outflows in the neutral gas phase. These are same data, as I mentioned before. Rebecca Davis was looking at the absorption lines from neutral gas, and she found that in 14 galaxies out of the 147, total, we can see a blue shifted sodium D detection. So we can see outflows of neutral gas from these galaxies. And all of the quiescent galaxies which show ionized gas outflows also show neutral gas outflows. So not only we're seeing ionized gas outflows, we're seeing multi-phase outflows that can, of course, be linked to AGN activity and feedback in these galaxies. How much time do I have?
7.
Oh, okay. I thought okay. Well, bonus. This was already discussed by my supervisor, I think, last year. So maybe some of you already know this, but there is one galaxy in particular in the quiescent sample, 11142, which shows a very powerful ionized gas outflows that are very easy to trace, and also in the neutral phase. So for this galaxy, we were able to get the mass outflow rate both in the neutral phase and the ionized phase from the absorption and from the emission lines, and compare it to the star formation history of the galaxy, which is the red histogram. As you can see, this galaxy had very intense but short-lived starburst phase, and then it had a very rapid quenching of its star formation. And by comparing the mass outflow rate gotten from the observed ionized gas outflows, we cannot really justify this very rapid quenching because the mass is not that comparable. But if we also consider the neutral phase, which of course brings with it much more mass, and we compare it, we can see that actually the outflows in the neutral phase are more than enough to expel so much gas from the galaxy as to quench entirely the star formation. And of course, this is one of the AGN galaxies, of the active galaxies. So this is a very important proof and link of this is an evidence of AGN feedback that is actively ejecting us from the galaxies and quenching the star formation. So this is the end. In summary, we have looked at a population of never before detected neuroluminosity AGNs at redshift around 2. And we have looked at also a subset of them, shows powerful outflows both in the ionized and the neutral phase. And no other mechanism is able to explain this outflows other than AGN feedback. And lastly, we can link these two together and speculate that the reason behind the quenching of star formation in this massive quiescent galaxy population at redshift 2 is due to AGN feedback. So this is still a work in progress, so I'm finished now. If you have questions, also suggestions, because I'm still working on this stuff, they're very welcome.
Questions for the speaker? Yeah.
Did you stack the X-ray emission just to have an idea of the velocity levels?
The X-ray emission?
Yes.
No, I did not, but I should. Okay, yeah. I didn't even think about it. Thank you. No, I didn't. So.
Yes.
Thank you, teacher. I was second. No?
Go.
Are you? Okay. So the spectra that you showed us, they look more like post Harbour galaxies, not like really quiescent galaxies. They have still do continue.
Yeah.
And I was wondering whether you define them in a plane defined at redshift 0. Or
well, I have let's see. Okay, we selected them using the rest frame UVGA colors, but actually since we were interested in looking specifically at the star formation quenching, we thought it would be better to also get the say bordering galaxies. So this is the typical used in literature division line, the green line, and we got a bit beyond, and we also got those that are staying there. And this is just a plot that I did that summarizes the different classification. But yes, that was basically by design. So yes, also we are at redshift around 2. So also the universe is quite young, and many of these, yes, now would be classified as post-starburst galaxies. But we don't have
the star formation history
from perspective. Yes, we have looked at them.
They show sign of recent burst of star formation.
Some of them, yes. Mostly the one, I think all four of the ones in which we have gas outflows show, I think, I have to check, but I think they all show recent bursts of star formation. But in general, also perspective doesn't go that far, of course, because we are also at high redshift, so I don't think it is really reliable after. I think it goes as far as 1 giga a year, but sometimes it is not that reliable. But yes, some of them are like the oldest ones in which there has not been a burst on star formation for a long time are the two classified as retired galaxies. Those are also one of the most massive, and they are the oldest ones in the sense of they have the oldest star. They formed the stars a long time ago before all of the other ones. But yes, there are many that could be classified as starburst, but they have a star formation rate that are very low, like under yes. They have very low, like under one solar mass per year, and also under one solar mass per year.
There were at least other two questions, but there was
Yeah.
a darker slide before, so I couldn't see where. One is there, yeah.
Nice lesson talk. I was wondering if the small percentage of real passive systems can be related to some intrinsic selection effect of the survey, or you think you have a complete sample of these systems?
Okay, the survey was designed to have a complete mass selection and also to have a complete redshift selection. So it was corrected for mass bias and redshift bias, but so it shouldn't be an issue, I guess. The fact is that for like I think here you can see the points without any contours are the ones that I was not able to classify. So we actually don't know. Like if we consider that a lot of this had a need an AGN, but we don't know. Well, we still don't know with those systems, mainly because the spectra are too noisy, or they're missing altogether some lines because they fall in the detector gaps. So I think it should be quite complete. Also, this classification here, I think like it's one of the things that I want to work on, because this let me go back to this classification here of retired galaxy is actually calibrated on redshift 0 galaxies. So it should be a bit worked upon, because we have reason to think that actually this limit is a bit lower at high redshift, because as you can see, the whole distribution is actually shifted a bit, because of course we are at cosmic noon, so we have in general a higher equivalent width of the CHR. But I don't think so.
Is there another? Yes.
I was wondering if you know if these galaxies that are classified as AGNs under their ratio, but they don't have the X-ray emission, if they don't have any detected X-ray emission at all, or if the X-ray is too low, so they are considered as low.
Well, in the two surveys that I checked, which are the Chandra Legacy Cosmos survey and the XMM Cosmos survey, they do not have any detection at all. Like you cannot, they are under the detection limit, I guess, of the surveys. So also the one that I showed you, like the really clear broad line AGN, is not detected at all.
We have checked also the images, so
we have. There are no images at all. Yes, it's quite strange. Yes, thank you. Yeah.
And I think connected to that, there is a question from home by Mari Polletta. Are they radio detected, and have you looked at the radio spectrum?
Well, I still am going through the archives, so I still have to check the radio. But like for now, like I don't know still. But
Okay,
I
there might
don't
be
think
some
they
radio
are.
in principle.
I don't think they are radio detected because I still have to check. There might be some radio detection. For one of them, surely like 11142, there is no radio detection. And but I have to check for the other ones. Yes, I'm going through all of the wavelengths. Yes, but
That's also-
yeah.
Any more? Yes.
I have a question on the UVJ selection. I think there is some evidence that in order to select clean sample of passive galaxies at higher redshift, above redshift 2, where you're working, the UVJ criterion that has been used up to redshift 1.5 or so should be modified. And indeed, if you move just a little bit to the red, your UVJ selection, most of your AGN objects would have not been selected. Have you looked at the possibility that objects like these are present also in other samples but were not selected, for example, at lower redshift because of such an effect?
Well, yes. Well, we use the UVJ, like not that strictly, to be honest, because as I already showed you before, we actually didn't even get the like real definitive line, but we also got a bit beyond that. And also the one that I showed you actually is modified to work at a high redshift.
Ah, okay, so you already modified.
Yeah, but in order to be sure, we also looked at the star formation rate. And this is the star formation rate of the sample. And in green, you can see the star forming galaxies, and in purple triangles are my quiescent sample. And apart from two outliers, which were also got catched by the BPT diagrams, we have that they are all falling below the star formation rate sequence. And of course, if many of these are actually hosting an AGN according to the BPT diagrams, so these are actually upper limits on the star formation rate. So they may be there may be a lot of post-starburst galaxy, but they have very low star formation rate as of like actual star formation rate right now. So they are not star forming.
Follow up quickly, because this is interesting. But also the DPT diagram that can evolve a little bit. Towards,
Yes.
And I was wondering, since all these galaxies are very close to the border of the green border,
Yes.
I was wondering whether some of them might be actually sort of liners, and so putting together the spectra that look like a recently quenched galaxy, together with this ionization that might come from all the stellar populations or shocks, might explain that maybe they are not AGN because they don't have a radio emission, they are not detected in X-ray. So maybe this can come from an older stellar population that is evolving out of the main sequence. Like I'm talking about
yes.
post-AGB.
Yeah, no, we have thought about it. Yes, of course. Like here, I have just theoretical evolution of because it is an observed phenomenon in star forming galaxies that the star forming sequence, which is basically the blue traced by the blue points, is evolving with redshift, and it is a bit higher at high redshift. You can see here, this is a study by Strom at 2017, and in red is traced the star forming sequence at redshift 0. And in like light blue is the star forming sequence at higher at cosmic noon, so around 2 redshift. And actually, we do see the same thing there. And and of course for shocks is a bit of a mess, because the shock can like shock heated gas can change well, can put your galaxy basically not anywhere but almost anywhere in the AGN side. But we have considered the fact that first, like there is a clear division between the two populations. Actually, there's only one star-forming galaxy that falls on the other side, and that's a broadline AGN also. That is
The one in the
the one
south
that's
middle?
kind of hidden there.
Ah, okay. Yes.
That's a broadline AGN that is also detected in the X-rays, and we have looked at that. And it's found in the same region as the other ones. And but of course, yeah, some of them could be due to minor emission. We still have to, like, the other plot, the one plot could be useful in that regard, because the one diagram, yes, because it kind of gives you a way to get the limit of ionization due to all the stars. But it would be interesting to recalculate that limit at higher redshift to check for this kind of thing. But for shocks, like the star formation rate that we got from H alpha luminosity is not high enough to like justify some shocks due to, for example, star formation feedback. So what other kind of mechanism is there that can, what?
Post HB stars.
Yeah, I guess.
Shock around,
yeah, no, it's still, yeah, it is still a work in progress. Plus, there is not much literature on quiescent galaxies in which we can do this kind of study. So, yeah, thank you.
Yes. No. Okay. Then we can take.